Welcome all of you to today's lecture in fluid mechanics. Today we will want to deal with the subject fluids under rest or rigid body motion. Fluids under rest. In this topic fluids under rest, there are lots of subtopics. That is, first is pressure and its measurement. Second one is hydrostatic forces on submerged bodies. Third topic is all about the flotation and different flotation conditions, metacenter, metacentric height. I will discuss all of these topics in different lectures. In today's lecture, we want to study about pressure and its measurement. And to know about pressure and its measurement, first thing you need to know is pressure and pressure head. And before you want to know about this difference between pressure and pressure head, let's understand first that what is pressure. Okay, let's first understand what is pressure and some important terms related to pressure. After this, we will study about piezometer and we will also solve a problem regarding piezometer. Okay, we will also solve a problem. So these are the things that I will discuss in today's video. Okay, so pressure is force per unit area. Pressure is an external phenomenon and its unit is Pascal, we all know. See, these two terms, why I have written it, because pressure can be expressed either in reference to absolute zero pressure or with reference to local atmospheric pressure. Okay, so what is absolute zero pressure? Suppose there is a system, it is filled with vacuum. What is vacuum? Vacuum means devoid of air, no air. It is entirely vacuum. Then the pressure of that system is absolute zero pressure. Okay. Next thing is local atmospheric pressure. What is local atmospheric pressure? It is very interesting thing. Suppose the room in which you are staying, what is the pressure in that room? It is by default local atmospheric pressure. What is local atmospheric pressure? See, we are entirely covered by atmosphere, different layers of atmosphere. Now those atmospheric layers have got some mass and due to that it exerts some pressure. Okay. Now local atmospheric pressure, it varies with altitude. It varies with altitude. It is maximum at the sea level, and if your altitude, suppose this is the sea level, and if your altitude increases, height increases, then the pressure decreases. Which pressure? Local atmospheric pressure, it goes on decreasing. Okay, that means people living in the hilly regions, there the local atmospheric pressure is very less. Okay, that's why water boils very quickly. It does not takes 100 degrees Celsius. Okay. Now, what is the reason? If you want to know that also I can explain. It is a very simple reason. See, let me assume two heights. One is this height and another is, okay, first suppose I am this height, this is h1. Okay, this is h1 from the, this height is h1 from the ground level. Okay, this height is h1 from the ground level, you can see here. Now there is a huge amount of mass of air present. Due to that it is exerting some pressure, and that is what I am calling as local atmospheric pressure. Now if my altitude increases, suppose now I am here, okay, at a height h2 from ground level, then the amount of mass of air above me, it decreases. Yes or no? That's why pressure decreases. So it is very simple to understand that why with increase in altitude, the local atmospheric pressure goes on decreasing. Okay, now we want to understand very two important aspects, that is the absolute pressure and the gauge pressure. Suppose there is a system, it has got some pressure P, then what is the absolute pressure? Absolute pressure is nothing but its own pressure, its pressure minus the absolute zero pressure. Okay, or the pressure at complete vacuum. If I assume that absolute zero pressure is zero, then absolute pressure is nothing but the pressure of the system. Now absolute pressure is nothing but the pressure of the system, that is P itself. Okay. Now what is gauge pressure? Gauge pressure is nothing but gauge pressure. Gauge pressure is nothing but the absolute pressure minus the atmospheric pressure. Absolute pressure minus the atmospheric pressure. Okay. What is the absolute pressure? It is P itself, because absolute pressure is what? It is the pressure minus the value of the pressure of the system minus the absolute zero pressure. Absolute zero pressure is zero, so absolute pressure becomes P itself. So P minus what is atmospheric pressure? P atm. This is nothing but gauge pressure. This is nothing but gauge pressure. I am giving you one example. Suppose the pressure of this system is P, but the atmospheric pressure is quite less than this value. Then the gauge pressure is defined as this. Now what is the use of gauge pressure? This gauge pressure is defined like this because we want to know that how much our pressure is more than the absolute pressure. Okay, I am having some pressure. Suppose this is my system. It is having some pressure P, but I want to know that how much this pressure is more than the atmospheric pressure. Okay, how much this pressure is more than the atmospheric pressure. So how much it is more? It is nothing but P minus P atm. It gives you gauge pressure. Okay, so gauge pressure, important significance, I want to know that how much the pressure of the system is more than the atmospheric pressure. But it may happen that the pressure of the system, suppose P, it is less than the atmospheric pressure. P is less than the atmospheric pressure. This may happen. In this condition, we call it as vacuum pressure. What is vacuum pressure? See, I am telling you. P atm, P atmospheric pressure minus P is nothing but P vacuum, or it is also known as vacuum pressure. Okay. Now this vacuum pressure is also gives you the relative value, that I know that my system is having a pressure P, and it is quite less than the atmospheric pressure. How much it is less than the atmospheric pressure? You subtract it, and that value is nothing but your vacuum pressure. Vacuum pressure is also defined as negative gauge pressure. Negative gauge pressure. Okay. Now we are ready to learn the difference between pressure and pressure head. Okay. Now suppose there is a system. Wait a little bit. Yes, suppose there is a system. It is containing some liquid, or you can say some fluid. Okay. It is having some pressure P. It is having pressure P. Okay. Now suppose what will happen if I just insert a vertical tube like this and just made a hole here. Now what will happen? This liquid will start rising up. This liquid will start rising up. Okay. Now, why this liquid has risen up? Because it has got some pressure. Because it has got some pressure. If the pressure of the system is more, then this liquid would have risen more. Okay. Can you understand? Suppose there is another system here. Okay. It is also having pressure P1. Okay. Suppose you don't know that which pressure is more. Then how to check? Just have one piezometer. This arrangement is known as piezometer. Suppose the liquid has risen up to this height. Which height is more? This one or this one? Of course this height is more. Suppose this height is h1 from here. If I take this height is h1, this height is h2. So of course h1 is more than h2. h1 is more than h2. That's why I can say pressure P is more than P1. Okay, or you can say this one P1, this is P2. So P1 is more than P2. Okay. This arrangement is known as piezometer. These are known as piezometer tubes. Now what are this H1 and H2? These are your pressure heads. These are your pressure heads. And this value it will be in meters in SI unit. Okay. Because H1 and H2 is nothing but the distance by how much this fluid has risen up in this tube. Okay. This H1 and H2 is known as pressure head. So we can write that this piezometer, it enables us to visualize. It enables us to visualize the pressure simply in terms of vertical height. Read this sentence once more. Piezometer enables us to visualize the pressure simply in terms of vertical height. See, I am explaining this sentence once more by drawing a simple diagram. Suppose there is a system, okay, it contains some fluid. I want to know that how much is the pressure in this system. How much is the pressure in this system? I want to know. Then I have got a very simple way to find it out. I will insert a piezometric tube and I will see that how much is the rise of the liquid column. How much is the rise of the liquid column? Suppose the liquid has risen by this much height, H1. Then what is the pressure? What is the pressure of the system? It is H1 multiplied by density of the liquid which is present here multiplied by G. That is H rho G. Okay, we know this. P is equals to H rho G. If I know this height, I will just measure by seeing it. And H1 rho G. Okay. Now see this height H1, it depends on P by It is P by rho g. It depends on the pressure, and all G is constant. It and also depends upon the density. Also depends upon the density. What I want to say is very simple. Suppose there are two fluids present in a system. Suppose this is one system and this is another system. Okay. Suppose it is containing water. It is containing water and this one is containing mercury. Okay, this is water and this one is containing mercury. Now both are having same pressure. This one is also having same pressure. This one is also having same pressure. Now the question is that if I attach a piezometer, attach a piezometer tube, then in which the level of the rise of the fluid will be more. Suppose there is a piezometer tube like this. Okay, I am telling you that the dimension of these two tubes are same. Area, cross-sectional area, length, everything is same. Now my question is that in which the level of the rise of the fluid will be more. Mercury will rise to a greater height or water will rise to a greater height. Pressure is same. Okay, pressure is same. Now in which case it will rise to a greater height. In this figure I have shown that water has risen to greater height, but the question is that I need to justify it. It is very simple. Just look here. H is what? It is P by rho G. H1, this is H2 is what? P by rho G. Pressure is same. G value is same, but the density in this case it is the density of water. In this case it is density of mercury. Okay. Which density is more? Density of mercury is more or density of water is more? Density of water is 1000 kg per meter cube and density of mercury is 13.6 into 1000 kg per meter cube. So this density of mercury is more. So this value is more, that means H2 will be less. This value is less, that means H1 will be more. That's why water has risen up to a greater height and mercury has risen up to a less height. For same amount of pressure, for same value of pressure, water has risen up to a greater height. Okay, that's why we can see that how this H depends on the density of the fluid. Okay. Now considering that we have understood what is pressure and pressure head, now we will solve a problem. We will solve a problem related to this. Okay. When you will solve this problem, more concepts will be clear to you. Okay. Till now if you have any problem, then comment in the comment box. I will try to help you out. So let's start solving the problem. Okay. Now see, there is a problem like this. You can see that there are different layers of fluid. First is air. Second chamber is filled with liquid 1, which is having specific gravity of 0.7. The third chamber is filled with water and the fourth chamber is with liquid 2. And through each of this, there is passing one piezometer tube. Okay, you have to find that the elevation of the liquid in the piezometer tubes. Okay, you have to find these heights of the liquid columns. Okay, you can see in the question here, for a gauge reading of A minus 17200 pascals, determine the elevation of the liquids in open piezometer columns E, F, G. So you have to find the elevations of the liquids in this open piezometer columns E, F and G. These elevations, okay, you need to find. and the gauge pressure is given as minus, the gauge pressure that A is showing is given as minus 17200 pascals. Okay, so we will start solving this problem, and these values 20, 11.6, 8, 6, this is nothing but the elevation, this is nothing but the height given. Suppose this 6 means that this line or this point or this region is at an elevation of 6 meters, you can say, from some datum level. Okay, this level 4, this elevation is showing 4, that means this is at a height of 4 meters from some datum level. Suppose you can consider your datum level to be somewhere else, somewhere here. So from here to here this height is 4 meters, from here to here this height is 6 meters, from here to here this height is 8 meters, from here to here this is 11.6, from here to this point it is 15, from there the down to here it is 20 meters. Okay, these elevations are given to you. Let's start solving this problem. Okay, so I'm keeping it here and solving it side by side. So first we will find this elevation, that is this L, that means how much this L is above the datum line. Okay, the elevation of this point L we need to find. The question, please read the question. Elevation of the liquids in open piezometer columns of E, F and G. Okay, so I'm writing the heading for column E. For column E, that means for the first column, see. First, see here, the pressure here, it is minus 17200 pascals. The gauge pressure is negative. What does this means? That means the pressure here in this chamber is less than the atmospheric pressure. Okay, the pressure here is less than the atmospheric pressure. So we can understand also that the rise in the level of this liquid one in this piezometer tube will not be more than this level. Okay, it will be less than this. Okay, suppose let me write this point, name of this point as H. H indicates this level. Okay, okay. Now see, since the pressure at H is below the atmospheric pressure, the elevation of the liquid in the piezometer E will be below H. This is the level of H, so the elevation in E will be below H, somewhat here, and I have named this L. And this distance is H. I need to find this distance first, H. So we know the principle of hydrostatics and we will apply that simple principle. See, it is very simple to understand. For column E, okay, P ATM minus 17200 plus 0.7 into 9.81 into 10 to the power 3 multiplied by H is equals to PATM. If I am doing for P at K is equals to pressure at L. See here, what is L? L is this point and K is this point. So these are lying in the same horizontal level and the fluids are same. Here also liquid 1, here also liquid 1 only. So I can write Pk is equals to Pl. That means pressure at K and L as same, because this K and L is lying on the same horizontal plane at the same expanse of fluid. Okay, the fluid at K and L are same. Remember this point. Okay, remember this thing. Now see, so what is the pressure at K? The pressure at K means the pressure at this region, at this level. Okay, it is the pressure at this chamber. What is the pressure at this chamber? The gauge pressure is this. So what is my absolute pressure? I am writing here, gauge pressure is given. So P absolute is nothing but P gauge plus the P atmospheric pressure. We know this thing. So what is P gauge? It is minus 17200 plus P atm. Okay, so the absolute pressure is nothing but P atm minus 17200. You can see here. That is what I have written. Okay, I want to find the pressure at this level, okay, this dotted red line. So it is nothing but the pressure here, the absolute pressure in this system plus the pressure due to this liquid column, which is nothing but H rho g, that is 0.7 specific gravity multiplied with 1000 to find its density into G, 9.81 into H. Okay, into H. H is this height. Okay, due to this H, or due to this level of liquid 1, there is some pressure, and that pressure is nothing but H rho into H rho G. Now what is the pressure at L? Pressure at L is nothing but the atmospheric pressure, because it is open to atmosphere. Okay, that is what I have written here, P atm, which is equals to P atm. Now someone may ask a question that why we have not considered the pressure of air due to this height. Why we have not considered H rho g for this height. Okay, my dear friend, I have not considered it because the density of air is very less, or you can say that specific weight of the air is also very less. That's why we are neglecting the pressure due to this height H rho g, but we are considering the pressure of this system, that is the absolute pressure, that we have considered. But what we have not considered is that this pressure, okay, due to the air column here, that pressure we have neglected. Okay, is it clear or not? So we have neglected this amount of air, we have neglected this weight of air. Okay, because specific weight of air is less. So we have considered the pressure of this system, that is P atm minus 17200, plus the height, pressure due to this height of the liquid one. This we cannot neglect because this is a considered value. Okay, you will get a good value, considerable value. So from this equation, P atm cancels out. So if you solve this, H will come 2.5 meters. This H, this small value, it will come 2.5 meters. Okay, now the elevation of point L, it is nothing but, this is 15, up to this the elevation is 15, so I am subtracting 2.5, 15 minus 2.5, that is 12.5 meters. Okay, so you can understand that this height of L from this datum level down here, I have shown here. See, suppose this is my datum level. So from this elevation, from the datum level to this point L, it is 12.5 meters. Okay, you have understood. Similarly, if we want to find the elevation of this point N, for this N, we need to find for column F. For column F, Okay. So for column F, when we are finding for column F, we need to equate the pressure at this region. Okay, the pressure at this point and at point M. Suppose I am writing this point as Q. Okay, not Q is written here. Suppose Q dashed I am giving. Okay, just for our sake of understanding. The pressure at Q dashed and M is same. The pressure at Q dashed and M is same. So equating that pressure, PQ dashed is equals to pressure at M. What I will get, see, now why PQ dashed and PM is same? Because it is lying at the same horizontal level and also it is lying at the expanse of same fluid. Here also the fluid is water and here also the fluid is water. Okay, is it clear or not? Now see, the pressure at this point is nothing but the pressure due to this and due to this. What is the pressure due to the air chamber? It is PATM minus 17200. Now what is the pressure due to this liquid one? It is due to this height of this liquid, due to the height of this liquid, which is nothing but plus 0.7 into 9.81 into 10 to the power 3 into, this is rho, this 0.7 into 10 to the power 3 is the rho, into 9.81 g into h. What is my height h? This height. Okay, this height is nothing but 15 minus 11.6. 15 minus 11.6. Okay, and what is the pressure here? What is the pressure at M? The pressure at M is PATM, the atmospheric pressure from the above, plus this rho GH, plus this rho GH. That means the pressure due to this liquid column from N to M. Okay, that is density of water is what? 1000 into 9.81 into H. Okay, 1000 into 9 point, so PATM cancels out. From this you find the value of H. You will get H as something 0.63 meters. Okay, this H means the distance from N to M. Okay, this distance from N to M. So what is the total elevation of N? Total elevation of N is 11.6 plus this distance. 11.6, up to this the elevation is 11.6 given here, plus you have to add the value which you just find out. So elevation of point N is nothing but it is 11.6 plus 0.63. Okay, which is 12.23 meters. Is it clear or not? Now for column G, we need to find this elevation. That means Q, for Q. How to find out this? It is very simple. I will equate the pressure at this point and this point. Okay, I will equate the pressure at this point and this point. See, let me write this point as R dashed. Suppose just giving it one name. Okay, so I need to equate these two pressures. So I can write it as P R dashed minus of P R. Okay, pressure at R dashed is equals to pressure at R, not minus, it is equals to that. Why these two pressures are equal, pressure here and here? Because they are lying on same horizontal level, and the liquid at the expense of the same liquid, that is liquid 2. Now what is the pressure at this point? What is the pressure at this point? Pressure at this point, or pressure at this region, is due to the pressure of here, here, here. Okay, so what is the pressure due to this air chamber? It is nothing but P ATM minus of 17200. Okay, what is the pressure due to this liquid 1? That means due to this height of the liquid 1, it is nothing but 0.7 into 1000, the density multiplied by 9.81 into what is this height? Height of liquid 1, it is nothing but 15 minus 11.6. Okay, I'm writing here side by side. And what is the pressure due to this water level? It is nothing but the density of water multiplied by G and the height of this water column, that is 11.6 minus 8. 11.6 minus 8. Okay, which is equals to the pressure at R. This is all about the pressure at R dash, which is equals to the pressure at R at this point. What is the pressure here? The pressure here is due to this liquid column from Q to R, that is nothing but liquid 2, that is 1.6 into 1000. Specific gravity of liquid 2 is given as 1.6 into 9.81 into this height. Suppose I need to find out H. Okay, rho GH plus PATM. What is, why PATM? Because this is open to atmosphere. There is some atmospheric pressure. So PATM cancels out. So if you find out this value H, you will get 2.64 meters. That means from here to here it is 2.64 meters. So what is the elevation of this point Q? The elevation of the point R plus 2.64. What is the elevation of point R? It is given here, 8. So it is nothing but 8 plus 2.64. This is coming 10.64 meters. This is nothing but elevation of Q. Okay, so I have found out the elevation of Q, I have found out the elevation of N, and I have found out the elevation of L. That means what? We have found out the elevation of the liquids in open piezometer columns E, F, G. We have found out this L value, that means for column E. We have found out this N value, that means its elevation, its height from the datum for column F, and similarly for column G also. The last thing that we need to find out is the deflection of mercury in this U-tube gauge. What is the deflection of mercury? This deflection is H1. We need to find out this H1. How much is its deflection? We need to find out this one. It is very simple. See, similarly we will apply the principle of hydrostatics between this point C and D. The pressure at C must be equal to the pressure at D. Why? Because these two are lying at the same horizontal level at the same expense of liquid. Okay, this liquid passing through C and D is same. Okay, from C to D here, it is same fluid, so we can apply this PC is equals to PD. That means pressure at C and D is same. Okay, so what is my pressure at C? What is the pressure at C? Pressure at C is due to this air, liquid 1, and this level of water, plus due to this liquid column. Okay, which liquid is flowing through this? Nothing but water is flowing through this. So water will flow through this. Okay, so let me write the equation for the pressure at sea. So pressure at sea, okay, it is, see here, it is due to the pressure here at A. What is A? PATM minus 17200 plus the pressure due to this liquid column 1, that is nothing but 0.7 into 1000 into 9.81 into 15 minus 11.6 plus pressure due to this entire water column. Pressure due to this entire water column. Yes or no? Or you can write it directly by, see here also water and the liquid flowing through this is also water. We can understand this. Okay. So we can write simple, that is P is equals to H rho G. What is the H value? From here to here it is what? See, this is 11.6 and this is 8. So this distance it is 11.6 minus 8. That is 3.6. Okay. 3.6 is this distance. And what is the distance from here to here? It is 8. This level is at elevation 8 and this level is at elevation 4. So from here to here it is 8 minus 4, that is equals to 4. So this total height of water column, this also water column and there also water column. So this total height of the water column is 3.6 plus 4. Okay. So 7.6. So I can write that the pressure due to this water column, it is H rho G. What is the total H? 7.6 into density, I know 1000, into G is 9.81. Okay. Instead of writing this and this individually and adding, I'm making it a single unit. Okay, very simple. Which is equals to this is pressure at C, which is equals to the pressure at D. What is the pressure at D? See here, pressure is at D is due to this liquid column, that is, this is water only, so 1000 into 9.81 into H1. Okay, plus there is some atmospheric pressure, PATM, atmosphere, because this is open to the atmosphere, it cancels out. So from H1 you will find it as 0.61 meters. Okay, so the deflection of the mercury in this U-tube gauge is 0.61 meters. This is the thing that you need to find out in the question, deflection of mercury in the U-tube gauge. I hope that this problem is clear to you, and this problem clears lot of other concepts related to pressure and how to apply these hydrostatic equations. Okay, thank you very much. In my next video I will explain you about manometers and solve some problems related to manometers. Thank you very much.